I always say if your business isn't simulating, you're standing still compared to your competition.
From Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. I don't want to play favorites. I love all the guests we've had in the lobby, but today's chat, the last one for season 4, let's just say it's very high on my list. I honestly could have kept listening to our guest for like 4 hours, but this is not the Joe Rogan experience. We try to keep it under an hour, but since this is the last episode of the season, we have a bit extra for you, and it's worth it. I'm even going to run out of intro music. Yeah, it's gone. Let's just start the track again. Our guest today is Bill Vass. He's the VP of Technology and Engineering at AWS, where his teams work on more than 42 cloud and edge technologies, working on applications from video rendering to robotics to data streaming and a few dozen more. He's also worked at the Pentagon. He was the CIO of Sun Microsystems and COO of Sun Microsystems Federal. And at another company, he helped create the first autonomous robot to cross the Pacific Ocean. Oh yeah, we're also going to talk quantum computing. This episode, it's going to have it all, so let's get going. Bill, thanks for joining me today in the lobby. I'm super excited for this.
Yeah, I'm happy to be here as well. Thanks for having me.
Thinking back, how did you know that technology and engineering was going to be for you?
I think as a kid, I was always one of those kids, I guess, learn and be curious that took everything apart. So I would suggest if you're a parent, and you have a child who's taking things apart, don't yell at them, give them more to take apart. And then I always had like building products like Legos and erector sets and things like that. And then one of my childhood heroes, of course, science sci-fi was Mr. Spock. And so he isn't just an engineer. And it's one of the reasons why I study biology and art and astronomy and physics in addition to doing computer science, because I like to understand things in a much larger domain and how engineering fits into that. And both the engineering of biology or the engineering that involves physics and those kinds of things. So I think having kind of that want to be like Mr. Spock, but also take everything apart. And I think when I went to college, my room would fill up when I'd come home after college with all the things that had broken in the house while I was gone. And I could just take them apart and fix them. That was like, I couldn't fix everything, but I could fix a lot of things. And that became sort of a common thing because in my job, I often have to fix a lot of things. So.
Different types of things these days, I imagine, though.
Yes, that's true. That's true.
What's your first memory of using a computer and maybe first memory of using the internet?
Yeah, so a friend and myself built a first very early stage computer ourselves with a kit that we pulled together. But my first use of a computer was a teletype machine when I was in middle school, just joined middle school. And it was an acoustic couple machine, and you stored all your programs and data on paper tape. And I still have those paper tapes, as a matter of fact. I saved them. So that was sort of my first interaction with a computer. And then, of course, later I owned a Commodore computer, with the tape drive. And I looked it up. It had 1,978 kilobytes could be stored on that tape. And then you got the 4K floppy was the most amazing thing in the world. And then, of course, we moved on to lots of other things as technology advanced. But the sort of the early days, that teletype machine was magical. It was writing in BASIC. And, you'd connect up to some mainframe somewhere and, you hear it go, and then you could save your program, write your program. It was very devastating when the tape would tear, though. You'd have to tape it back together and put holes in it so that you didn't lose any of your data or your program.
Yeah, what an era. I'm glad we don't have to do that anymore.
I know.
And then you are the second Aggie in a row that we get to have on the podcast. So, and I went to A&M as well, so we're going to slowly take over the world here.
That's right. Yeah, at A&M though, in college, we were all on a Wilbur mainframe back then. And we stored things on cards, right? That was and then the very first 300 baud modems.
So it sounded like you were doing computing at A&M. What did you study and what did you major in?
My primary major was in geology, actually, because I never thought people would actually pay you just to do computers. I always thought it would be using computers for other things. So I studied marine biology, geology, and computer science. Those are sort of my three areas of discipline at A&M. And I worked in the computer lab there and the Wilbur systems as well, and worked on the help desk and, worked loading printers and all sorts of other things like that. And I had a Commodore VIC-20 and then a Commodore 64 at home that we could connect into. And I helped to work on the 3380 storage drives for the mainframe. A few of my friends had Apples at the time. That was the early days. We also had a Trash 80 and a Sinclair machine. Probably no one remembers what those are, but and then I started carrying back then which I also used in my first job, the IBM yellow card.
Nice.
I don't know if you remember those, but the yellow card had the ASCII and EBCDIC translations, so you could, when you had an event dump, you could figure out the offset address in memory of where the code was, where it had crashed, so you could fix it.
I had a roommate in college who had a like computer lab day shirt, and it had a bunch of like Python commands on the shirt printed upside down, so he could look down and get his.
That's really smart.
Reminds me of that.
That's really smart. Yeah, those 3380 drives were magical back then too. They were 2.5 gigabytes, which was amazing, and they weighed 550 pounds.
Whoa.
And then we had all the tape drives as well, and I still have done so much with tape throughout my career as well, which is kind of amazing.
So, when did you realize that computing itself could become a business instead of just a means to an end?
I found myself working as a data processor and programmer at Western Geophysical. Well, first, I paid for college by working on seismic vessels, running the computers on the ships. And then I would also follow the tapes that were recorded there back to the data processing center. And then I started working on the software to do the dip move out corrections and the gains, a bunch of math, fast Fourier transform, mostly in Fortran, GL1, and a thing called C-List back then that we used kind of on the mainframe. It was a IBM mainframe at 3270 with a vector array processor, one of the first vector array processors out there. And I was doing 2 and 3 dimensional models of the Earth using Versatech plotting routines. And you would do it both in the graphics and in real on paper, and then on this film that we would print out in. Then basically from then on, I didn't do anything but computer stuff. I just moved from doing that in the oil and gas industry to doing it in the defense industry, then doing it for information technology companies and others, along with robotics and things like that. But it's, it just ended up, that's the only thing I ever did was the software and the hardware, right? I never ended up doing anything else but the software and the hardware. But initially it was to do geology, which was pretty interesting to see the Earth rolling out on these big plots of what was happening in the subsurface and all the tectonics and the faults and the bright spots where the oil and gas would be and things like that. But it was a tremendous amount of math basically that you were doing to do that. And so the computers were pretty key.
Do you still have any of those old computers sitting around the house? I know a lot of folks have hung on to them.
I do. I still have my Commodore 64. Like I said, I still have my paper tape from my first programs I ever wrote. I still have some 6250 tapes of software that I made backups and brought them home because I didn't trust the company to keep losing tapes. And so I would bring backup tapes of my software home so that if they deleted all my source code libraries, I could restore it myself. I still have a lot of those things, in the barn.
So how would you describe the progression of cloud and edge technologies as time has gone on? It went from just, you were on a ship as the computer guy into now that maybe, you could probably do that from the comfort of your home office. How have you seen that progress over time?
Well, so technology runs in a 25-year cycle. And so it's kind of a cycle of centralized and decentralized, centralized and decentralized. And a lot of it has to do with networking technology and user interface technology. And so as user interface technology increases, then things have to run locally. And then when the network catches up, that moves back to a central thing, and then it moves back again. And so if you want to look at the future, you always look at the past. So we're kind of, in some ways, reinventing the mainframe with the cloud, right? And in some ways, it's always getting better. So you can imagine there's a sine wave that's always getting better, right? And so I always look at a lot of these inventions. If I want to look at what the future is, I'll take a look at the past and say, well, this is the way it's going to go, right? I know that edge will continue to grow because that's, I know the cloud will continue to grow as well, because I know that those cycles are happening over and over again. Right. And so you can kind of see how things fall into place. I mean, history does often repeat itself, and unfortunately, we don't learn from it. So I think in a lot of cases, that's an important part, I think, for any engineer, is to take a look at history and kind of understand it. That's kind of also why it amazes me that today we don't connect art and engineering in education, because it was always connected in the past, and now we think of it as two different things. But the best engineers I've met are artists. The best coders I've met are artists, musicians, and architects, and artists that also know computer sciences, right? So because they kind of care about doing it the best way, how it optimizes, not just writing the code and getting it out as fast as you can. And so I think that's one of those things that you have to kind of look at is take a look at the past to predict the future.
And if you've looked at our past episodes, you'll know that the future of the next 30 seconds is a quick break. We'll be right back. This podcast is sponsored by EBV's podcast, Passion for Technology. Ready for the next level of optimizing your ears? Techies, watch out. Their new podcast, Passion for Technology, is dedicated to the latest technologies, trends, and applications in the electronics industry, such as a podcast series on analog and power management. There are already 3 out of 6 exclusive episodes available. Listen also to the recent episodes on silicon carbide and gallium nitride, wearables, EV charging, UV LEDs, edge computing, and robotics. Tune in now and dive into the world of semiconductors. And don't forget to follow the Passion for Technology podcast on your favorite podcast platform. And now back to our chat with Bill Vass, the VP of Technology and Engineering at AWS. Going off on a tangent here, have you seen the AI generated art trend that's been happening with like DALL-E 2 and all that?
For sure.
What are your thoughts on that and how that technology and art blend together?
Well, I think that it is fascinating to see how algorithmic applications of scalar vector models can generate those kinds of common, what we would call art. But it's basically doing the same kinds of things like when we look at clouds and see a clown, right? In a lot of ways, right? So it's kind of repeating that image processing. Again, we tend to, this is why I like biology as well, we tend to repeat in the way we design machines and algorithms what occurs in biology, because that's what we understand. And that's also one of those areas where, when we talk about computers being self-aware and things like that, it's very, very hard to do because we don't know how we're self-aware. So we can't really write the code to be self-aware, right? We understand how neural networks work and other things like that. So we can build scalar vector models, which is just math to do the neural networks. And we can apply the weighting and all those things that you do and the density in the models. And the more data you provide to a model, the more dense it is and the more accurate it becomes over time. That's why we do things like we just launched ground truth synthetics, which generates extra synthetic data for you in addition to what you could create to make more dense models and make them more accurate. But and I always think of, the batch processing that happens at night is probably very similar to how our brain works when we're dreaming and we're kind of associating everything as we sleep and storing it away in the right places. And then how we also work interactively. I think we design these machines based on how we understand and how we work because it's the only thing we can do, right?
Yeah.
But I think that's a challenge in making a machine self-aware is we don't really understand why we're self-aware, so we can't really write the code for it yet. So
I was watching my 2-year-old run around yesterday, just thinking how amazing it was that you could go from like this bundle of cells into this thinking being, and like what a mystery that is. It makes sense, especially in the context of like the Google AI, where the engineer is like, it's sentient, and everyone's like, nah, it's not really.
We spend a lot of time on quantum computing, which I know we'll talk a little bit about later, but that uses a thing called entanglement to do your processing. And if you talk deeply with some of my PhDs in quantum computing, they believe that consciousness is entanglement between the neurons in our brain.
Oh, interesting.
And that it's an interdimensional thing.
Whoa.
So maybe with quantum computing, we can make something that is self-aware eventually. But we don't really understand that, right? So you can't say that that's factual. That's sort of like their opinion in how our brain works. And that's really fascinating because entanglement is an interdimensional physics, right? So
Yeah.
it's fascinating to think about.
I think I need just like 5 minutes of silence to process the last 5 minutes. Fascinating.
Yeah,
So let's move on to kind of what you do, because you work on so many different technologies.
yeah,
I have in my notes 42 different cloud and edge technologies.
yeah.
How do you, as a single person with a single brain, keep up to date on everything that's happening in even one of those verticals, let alone all of those? Can you kind of outline some of the things you're excited about?
Yeah, so I've always, like, when I was one of the CIOs at the Pentagon and one of the CTOs for the Army, I always worked on kind of two different areas. One was like really the core components of the systems, the governance, the management, the storage, the compute areas, and then I always worked on emerging technologies, nanotechnologies, quantum computing, satellite systems, those kinds of things. And I always kind of segment those into two different areas. And we kind of look at that way here at Amazon. We've got sort of three different types of technologies that we might be working on. We'd be working on an established technology that everyone understands that runs in a data center. And those tend to grow very quickly, and they're really easy to move to the cloud, like an FTP as a service or a NAT gateway, or move a virtual machine from on-prem into the cloud. Those are really easy concepts for people to move and understand, and they understand that they would run in a data center. And then there's other types of technologies where, like, you're creating a new market that's never been possible before the cloud. Machine learning is in some ways follow that. I mean, machine learning, my first experience of machine learning was in 1978, trying to run a neural network for navigation of an autonomous underwater vehicle for an ocean engineering company, right? So that goes back. It really hasn't changed that much, except for we have a lot more storage and compute. Right, to do the same math, so it becomes much more viable now. So our team, one of the services our team created was Kinesis, which got popularized as Kafka became popular as well. And I remember going to customers and saying, "Well, this is streaming." And they're like, "Well, I don't do video." And I'm like, no. Streaming, like, is streaming data, as in things that are constantly changing in real time. And trying to get people to understand that with the cloud, with the millions of servers and threads you can have in the cloud, you can move from temporal processing and knowing what happened yesterday, like in an elastic map reduced or a database, to knowing within seconds of what's happening in real time, doing that processing in real time. And so we had to kind of create that market. That market didn't exist. People didn't understand it. Of course, now it's very well understood with Kafka and other things like that.
A quick note, Apache Kafka is AWS's streaming data service. They let you publish and subscribe to streams, store data streams, and then process those data streams in real time. All right, back to Bill.
And then the third group are services that don't run in a data center or the cloud today. So people don't think about it as being cloud enabled. So an autonomous vehicle, for example. But an autonomous vehicle is extremely bound to the cloud because you're doing the millions of miles of training every day in the cloud and then pushing it, but it has to execute locally. So people don't understand, or robotics or drones or other things like that, or quantum computing. These are really emerging kinds of things. So I kind of look at the services in those three different areas. Well, I'm working on a storage service that's very well established and understood, and really the big innovation there is, how do we run at our scale with, huge numbers of transactions, huge volumes of storage? How do we add all the features that people expect in storage? Storage is well understood. If you move to things like Kinesis, that's pretty well understood now, or Kafka, that's pretty well understood, but there's other things coming in those areas, data sync, or there's a whole bunch of different products in those areas, IoT and others. But IoT is kind of a mix because there's the back end and then the front end. The front end happens outside the cloud, and that is kind of on this, and robotics on this edge, right?
Yeah.
And so I kind of segmented into those three different areas as to how I'm going to spend time. And then I also spend my time, I graph my calendar out. I know that sounds pretty geeky, and I break it into
That's awesome.
the amount of time I spend on engineering, on marketing, and on sales, and then also the amount of time I spend on people, process, and technology. And so if you were to do a pie chart, you'd want an equal 1/3 on people, process, and technology. right? My natural tendency is to spend most of the time on the technology. But I highly value process and people. So I have to force myself into the people and the process side to balance that out. And then between engineering, marketing, and sales, I have to spend equal amount of times on those as well. So that's sort of the way I look at it. In sales, obviously, I'm working with customers, but with customers, I often find people like, oh, Amazon is so inventive. They're inventing all these things. We really just listen to our customers and build what they tell us.
I find a lot of people think they're listening to their customer, but maybe they're just building what they want to build. You obviously have been quite successful listening to the customer and building what they want. So what does that look like for you? What's maybe a couple examples?
It sounds so simple, but it's like you meet with a customer and they're like, gee, I have all this data, I can't move it over the cloud. How could I move it to you securely? But it's going to have to be secure, and I can't worry about address labels and all this other stuff. So we build a snowball that turns into the ability to transfer the data physically, right? Or I have this problem where I want to do, FINRA wants to do real time a fraud detection in transactions occurring, SEC kinds of transactions, things like that, trades and other things like that. And so then you have Kinesis, and then you have the ability to run Lambda on Kinesis as it's processing in real time and be able to do those correlations in real time, right? So then you're building that. So customers want to connect their car and manage their car remotely and update their car. So then you're like, okay, what's going to run in the car? What's going to run in the cloud? How can I connect that securely in those areas? And then you do have to kind of understand the emerging technologies in all these areas, whether it's nanotechnology, MEMS technology that's occurring that affects these things, different material sciences that you will see with quantum and other things like that, piezoelectric resonance chambers on chips, and like those
crazy things.
Yeah, crazy things that you don't think about. How all these trends come together, along with the macro trends that I mentioned of the 25-year cycle, right? So you've got what's happening with 5G. Where is 6G Wi-Fi going to go? How are those going to get managed? Well, geez, as Kuiper comes out, how's satellite communication going to be working for that? Where is processing going to occur in space versus on ground, right? Back to this edge, like where are you going to decide what's going to be on the ground, what's going to be in the car, what's going to be on the robot, what's going to be in the cloud?
Yeah.
So you kind of rotate between these areas, but there's a lot of commonality across these services. They don't often sound it, but for example, you've got this emergent simulation everywhere, and you've got this emergent 3D processing occurring everywhere, and then that is all being done for predictive analytics, which will be helped with quantum computing, and material sciences, molecule simulations will be helped with quantum computing, and then you've got the edge processing with robotics, space processing and things like that. Then how are you going to communicate? And you have to deal with lossy communications and all those things. And then all of that comes back to these huge data centers where you're worried about space wattage and power, and how you're managing space wattage and power to the most efficient way. And as we transition to green technologies, where quantum computing, again, will make a big difference in the future in the material science side.
There's a lot of variables there. It sounds like a great job for someone who is so into analysis they analyze their own calendar.
I don't know if I'd say I'm so into analysis, but I do analyze my own calendar and how I spend my time. Because you manage what you measure, so you do have to measure things, right?
Well, I'm definitely all about the measurement game. Let's take a quick break. We'll be right back. This episode of Moore's Lobby is sponsored by the Exponential Technology Group, part of TTI's family of specialists who's an expert in all things IoT. XTG's engineering team can literally take an idea from the back of a napkin and produce a full product design, from the proof of concept level to software development to cellular carrier specifications in their in-house RF lab. They've been designing wireless devices for marquee customers since before IoT was even an acronym, and as part of the TTI family, they are attached to one of the largest inventories of electronic components on the planet. The latest information on product lead times and availability is considered throughout the design process, and as soon as your bill of materials is fixed, they can pipeline inventory to support your production ramp. Utilize the support of XTG's engineering team to streamline your next product development project. For more information, visit exponentialgroup.com/EETech. That's exponential spelled XPONENTIAL group.com/EETech. Now back to Bill Vass, VP of Technology and Engineering at AWS. There are a lot of terms around cloud computing. What is extended cloud? That's one I haven't heard before.
Where you're extending it to the edge. Our goal ultimately would be that you could build something in the cloud, simulate, test it in the cloud, and then push it to where the lowest latency and least network is used at any time. It isn't like the cloud is going to get less powerful, and it isn't like your end devices are going to get less powerful, right? I mean, we do have like FreeRTOS, which is this tiny MCU platform operating system combination, now does symmetric multiprocessors. I never thought I would say that, but now we've got devices running sort of an MCU environment that's got more than one processor in it, and so that's going to continue to get more powerful. And I think developers are going to leverage it sort of end to end, take advantage of the cloud where it's really useful, take advantage of edge processing where it's really useful. Our goal is to make that easy from edge to cloud.
You've used the term snowball a couple times now. Can you explain, for those unfamiliar, what snowball, snow cone, kind of what's going on with that?
So there's one here. So you can see it. So basically, you can think of it as a ruggedized cloud appliance is probably the best way to think of it.
At this point, Bill is holding up a gray box about the size of like a modern digital multimeter, like benchtop size. It fits in his hand. He can turn it around pretty easily. It's gray, kind of like test gear. Just to give you a little context here.
So this is the snow cone is the smaller one. So it's under 5 pounds, and the snowball is a bit larger. It's under 50 pounds. And so it's a combination of compute. So this can have up to 16 terabytes of storage on the snow cone, and then it's got 4 x86 cores in it for processing. So you can run little EC2 instances on it, containers. It's got a little S3 API compatible component. It's got file and block storage and those kinds of things. And it can run disconnected for years if you need to. We just put one of these on the International Space Station. So as you can see pictures of it floating around the International Space Station. And in that case, they're doing edge ML processing and collecting data that will be shipped down. So the Snow products have 2 use cases. The first use case is ruggedized edge processing and disconnected processing. So you can, again, build in the cloud, define your cloud formation template of all the apps you want to run, push it to the edge. And the larger snowball can have, hundreds of x86 cores and thousands of GPUs and 100 terabytes of raw storage and 100 gig networking and all that stuff in a little box that you use. They have an e-ink label on them because they know where they're going and they can automatically ship themselves. They interface with all the common carriers. The snowball is under 50 pounds, so you can check it as luggage without paying an oversized fee. And all common carriers can ship it, and it meets OSHA standards for one-person liftable. They have can handle huge impacts. You can airdrop a snowball with a parachute, and it can handle the impacts of that, hundreds of Gs and the impacts of that. The snow cone, for example, handles all the Gs of space launch. It's space certified without any changes to it. So it can handle a lot of Gs. They are moisture resistant, so you can leave them out in the rain and things like that. They don't get hurt. They can handle very high temperatures and very low temperatures. So in these rugged environments, they have 3 layers of anti-tamper on them and 3 layers of crypto protection. And they run a trusted operating environment, super paranoid, from a security perspective. So they meet what's called Authority to Operate TSSCI Level 6 Plus, which means that they can operate with top secret secure data for the intelligence agencies and the military. It is the highest security standard in the industry. And so they are extremely secure devices for shipping data. So the second job, of course, of a snowball is to ship data. So you can, if you need to exit your data center, for example, and you don't have enough bandwidth to move all your data fast enough, you can order the snowballs. They will arrive. They will download all your data. The e-ink address will change to one of our ingestion centers automatically at the end of the download. You'll throw them back on the loading dock. all the data is triple encrypted, and the third key stays in the cloud. They arrive back, everything is hashed and checked, that nothing has changed in transit, and then the data is unloaded into the cloud. And then the snowballs, refished with a NIST standard wipe to be reused for the next customer. And the next customer, orders it and does it again. So they're used for, anytime there's bulk data. They're used a lot in the movie industry for collecting big movie shoots. The snow cones are heavily used for photogrammetry, data collection, for doing 3D modeling and things like that. They're used for ADAS data collection in cars, those kinds of things. The reason this is under 5 pounds is it's designed to be carried by a drone for 3D photogrammetry. Anyway, people can Google on YouTube and look at a whole bunch of videos of me showing snow cones and showing them getting, they pass the DoD 901 barge test where they have to survive multiple explosions of the equivalent of a depth charge. And you can see them getting blown up and surviving the explosions and all that stuff. So they're a pretty fun, ruggedized device. It's really, this goes back to us building what customers ask us for. Customers ask us for something where they could feel comfortable about shipping their banking or HR data or top secret data back into the cloud. They wanted to make sure that it couldn't be put in the wrong box. So it is its own box, right? That's why it's ruggedized for shipping. And that they couldn't put the wrong label on it. So that's why it generates its own label.
Fascinating. I feel like I just listened to like the montage in a spy movie, but like for data nerds.
Yeah, so it's gray. Can you guess why it's gray?
Well, it looks just like the HP boxes that I have all over the place, the old test gear. Thermal?
This is called cool gray. So if you leave it in the sun, because these are used outside, it won't absorb heat.
Okay.
The marketing people wanted to make it black because it's cool. Black is cool, but black is not cool in the real world.
Yeah, I've seen mixed reception on black industrial design.
If you ever had a black car, you understand what I'm saying. As far as black, it is infrared reflective.
That's a nifty little box.
Yeah, and it's cool, and you can use those for $6 a day, so they're really cheap to use. You use them, collect your data. A lot of people use them for video shoots and things like that, and then just send it back in, and then it gets uploaded to the cloud for you.
So I imagine there must be some sort of cloud storage or offloading costs associated with it as well, but clearly it's not enough for people to stop using them.
Storage in the cloud is very cheap, generally speaking, but the edge compute also is an area where people keep them for long periods of time in ruggedized environments. They're used a lot by the military and others, oil companies and other things like that, where they'll keep them for months or years at a time. And they're doing that edge processing they would do in the cloud, but they have no network. So they will build in the cloud, deploy on the snowball, do that processing at the edge. And then the other nice thing is they're not buying hardware. So like the cloud, the hardware is always getting refreshed. Every time they order a new snowball, they get the latest and greatest hardware, right?
Yeah.
As we refresh the fleet in that. Just like in the cloud, you're constantly getting the CapEx is being refreshed in the cloud, which you can't necessarily afford to do on-prem. And so you always get the latest and greatest sets. We're always doing, speed bump improvements and storage density improvements and network performance improvements on each iteration of the Snow products as they come out.
Okay. That makes sense. Yeah. As someone who does video also, like trying to travel and shoot is a nightmare. So it's like,
Yeah, we do have people who use these for video shoots. So you could like pre-order one, and where it arrives where you're traveling, you could download all your video onto it and then just throw it in the mail. And then it would be uploaded to the cloud where you're done. So like, wedding videographers use it because they're doing 4K video now and things like that. And, it's a nice little device. It's got, Ethernet and USB ports on it and Wi-Fi and other stuff like that. So it's like a little server basically that's ruggedized and can be shipped.
Doing a terabyte on a shoot is like a normal thing. Like that'd be nothing.
I know. Yeah. So 4 terabytes is not unusual. And for our automotive customers, about 8 to 10 terabytes per drive for their test fleets is pretty common. And it just takes forever to upload that over the network, right? Oh. So you just throw this in the mail, and the next day it's in the cloud, and then you can edit it and do whatever you want with it. So it makes a lot of sense for those edge locations, right? I mean, that's pushing the cloud to the edge. That's what it's about.
I'd like to shift gears a little bit so we don't run out of time. I've heard simulation mean a lot of different things to a lot of different people. What does it mean for you and AWS?
Yeah, well, I always say if your business isn't simulating, you're standing still compared to your competition. And because that's, I mean, a lot of what we've always done with computers is simulate. We talked about some of the examples earlier, right? Nowadays, you're seeing simulation kind of converge around machine learning, training, and business optimization and digital twins. So those kind of fall into those different categories. So, for example, Twin Maker today is really focused on having a digital twin of your operating environment or a car or a person or whatever you're building a digital twin of, getting real-time data in and having situational awareness to understand how that's operating. And it integrates in video and other things like that. So you can turn the cameras on the shop floor and see what's really happening. You can get the IoT streams in real time. But for each item that you define in there, we allocate a compute instance for it that you can put a simulator in. And so you can feed the IoT data into that simulator, and it will tell you based on what that manufacturer says how often you need to change the oil or change the bearings or whatever. So you can predict it how often you need to maintain all the components in your smart factory, right? What will happen in the future is sort of hanging those together to be able to simulate the entire end-to-end factory operations or any of those kinds of capabilities. And then you can start optimizing your smart factories and then save money basically, and then be more and more efficient over time.
Okay.
And so simulation kind of falls into this business optimization, whether you're simulating logistics or you're simulating, your factory operations, or you're simulating, a car crash while you're trying to design a car, from design simulation, those things, to simulating whole virtual worlds where you're having a car drive around in it, and you can do, say, 15 million miles a day of driving in the simulation that you could never do in the physical world, or drones, or we have a product called World Forge that'll generate random houses for you. You can drop your vacuum in or your robot in and simulate in those random houses with each release. So like iRobot uses that, for example, with RoboMaker as they simulate, or really advanced machine learning simulations where you're, for example, with SageMaker Ground Truth Synthetics, we're taking photorealistic rendering. You take 3D models and you're rendering it in every possible view with every possible light for the sensor, so the robot can do grasping plans to pick up those items. And so instead of doing like one human sitting there and doing 10,000 or 30,000 photos and saying it's a box over and over again, then feeding that into a model, you create one 3D model and then generate that in hundreds of thousands if you need pictures in all different lighting and things like that. And a lot of the simulation that's happening now is kind of converging on sort of the three gaming engines are getting to be used there, right? So you've got, Unreal from Epic, you have Unity, and then you have the open source O3DE, and things are converging on those three engines to be used for simulation, just like they're also being used to do movies, where movies are sort of a simulation when you start doing CGI, or they're being used for training simulations or AR, VR simulations, those kinds of things. So simulation is going to be a big use case for the cloud. And I think it's going to integrate a lot with the edge to visualize those simulations or the simulated worlds.
So you were mentioning video game engines and simulation and kind of like dropping in houses. What is your thoughts on the metaverse? Where is that going, and how does AWS play into the metaverse?
Yeah, so if you remember back in the 90s, when video on the web was just starting and you kind of saw the promise of it, we're experiencing the solution of it today, right? And kind of the maturity of it today. You see 3D processing on the web sort of starting now. It's been around for a few years and it's starting to evolve. Things like, if you go to Reddit, you can do a 3D tour of a house. Right. You don't need, 3D goggles or anything to do it. You can put those on and you can get a more immersive experience, but you don't need it. But you're going to see travel sites doing that. You can imagine that, every product on Amazon, I'm not committing to this, just to be clear, but I can imagine that every product on Amazon, you'll be able to rotate it in 3D and look at it, right? And that 3D processing is going to become very pervasive. That's your foundation for what we start to call the metaverse, right? And we think that there will be these 3D immersive environments, but they lead to the foundation for simulation, for simulating the real world. They lead to virtual training, the ability to put on the AR, VR headset or to use it. And I think this is really important. If you don't get anything from the conversation in the metaverse, it's that it's 3D processing and the ability to simulate the world in 3D and link the virtual and physical world together. It isn't AR, VR headsets, right? Those are just another input output device for interacting with 3D environments. We've been doing 3D glasses. I worked on the first 3D caves when I was at Sun Microsystems, where it was interesting. We had projectors, so the floor was translucent and all the walls but one were translucent, and we had like 60 projectors that would project onto those walls, and then you would put on these glasses that had an LCD flash back and forth to give you the 3D feel. And you could walk around, and we would use it for, say, designing ships and things like that. You'd walk around the inside of a ship for the Navy, and you'd see in 2D, you could see like the engine room, but in 3D, you could see you would hit your head on a pipe, right?
Sure.
If you walk on the pantry, so you could change that and interact. And we've been doing that. That was, in the 90s, right? So we've been doing that for quite some time. But like all things, those continue to improve. And I think when I think of the metaverse, I think about 3D assets. I think about the 3D mapping that's occurring, allowing you to import like San Francisco and walk through San Francisco and walk through the streets of San Francisco. Anyway, and then you see this idea of augmented reality where you could have your phone, you could hold it up, and you see kind of this with like Pokemon Go and some of the stuff that Niantic is doing. You can hold your phone up and look around, right? And it's got it's overlaying the virtual world on the physical world, right? And you continue to get more information. But I think that works fine on a tablet. It works fine on a laptop. It works fine on a TV set. It works fine. It doesn't require the headsets. But I think there will come a time when these 3D headsets are as nice and lightweight as the glasses you're wearing right now. And I believe that processing will occur by streaming from the cloud and also using your phone as a caching and processing local device, because you won't want to put all the processing on your glasses because you won't have room for it. And the other big problem is the battery, right? But I think you'll have to have today a high-speed wire connecting your glasses to your phone. The Wi-Fi and Bluetooth will cause latency and tearing right now. We may have higher speed wireless coming that will solve that problem as well. But I think the early units, if you take a look at the new Oculus, it's pretty impressive. I use it at home to interact with virtual worlds, but I can't imagine people walking around the streets with those on. I can't get my wife to wear it, right? So I mean, you got sort of that kind of a challenge. But I think that there will be advancements, just like everything in microelectronics, where they will become as lightweight as the glasses you have on right now. And people will use them much more pervasively. They won't look geeky. They'll look like just normal glasses. But I think the 3D processing is what's most important, and the link between the physical world and the virtual world, that's going to be most important in this discussion, not the headset.
I'll be honest, I'm ready to ditch my headset. So let's take a quick break. We'll be right back. Hey there, this sponsored spot's going to be a bit different, so bear with me. Picture a big pot of delicious stew. It's steaming, it's been cooking for a while, but it's not quite ready for consumption. It needs to cook a little more. But there's something weird about this stew. It's not food. The ingredients are prizes. Industry experts from companies like AMD and Intel. The broth is engineering best practices, and the pot is a virtual engineering event. While that might be the worst metaphor I've made in a very long time, that's kind of where Industry Tech Days 2022 is right now. Our team of engineering chefs is working in overdrive to get this event ready for you. This stew won't be ready for signups until August, but you can be the first to sign up when it's cooked. Just go find the link on this podcast episode's webpage and follow All About Circuits on social media. I'm hosting the keynotes again this year, and we have big prizes simmering. I won't spill the tea, but last year was a big lab kit with a bunch of test gear and soldering goodies, and 2020 was a commercial grade 3D printer. So you might regret sitting through my bad metaphors, but you won't regret signing up for Industry Tech Days 2022. Go find the link on the Moore's Lobby page, and let's get back to our podcast. So Bill, I understand that AWS is heavily involved in the industrial realm, and you've even gone so far as partnering with Siemens and some other folks. What does that look like for you?
So, one of the nice things about working with AWS in the industrial space is we build a lot ourselves. We build devices ourselves. We run large fulfillment centers. We run large logistics. We run over 520,000 robotic heads or robotic units. So we have to do this for ourselves, and we understand it well. So as we move into the industrial space, the other thing we do incredibly well is security. We run the intelligence agencies, clouds, and things like that. So we're certified for the highest levels of security and have been longer than any other provider. So security is really important as you look at any of these industrial applications. And as we move into, working in smart factories and those kinds of things, you have the advantages of our machine learning capabilities, both what we've learned in doing ourselves, things that we've done with advanced machine learning for vision and robotic planning and robotic management. You get to take advantage of things like RoboRunner, where we're working on having robots that are made by heterogeneous manufacturers work together that we have to do for ourselves, so we can bring that experience to you. Things like RoboMaker, which we have to do for ourselves to build the software for your robotics. And then things like TwinMaker. We had a lot of customers say, I want to build digital twins of my smart building, my factory, those kinds of things. So we created TwinMaker, again, listening to our customers, and we continue to evolve and advance that. And one of our strong partners in TwinMaker is Siemens, because Siemens has this deep industrial expertise. And so where we kind of work together there is we have, we do the heavy lifting of the transport layer, the over-the-air software updates, the IoT data. We can handle billions of devices. We can handle hundreds of thousands or millions of devices on site at our scale. We can, securely tunnel that information in. We can store it. We can manage it. And then Siemens brings the industrial expertise, right? The expertise of, how they've been working in the industrial space for a very, very long time. They understand SCADA systems and program logic control units. They understand, factory floor automation. They understand automotive automation. And so we have a very tight relationship with them where we're really focused on, if you like, the cloud components, securely communicating, transporting the data, being able to display the digital twin, being able to apply the machine learning to make it easy to do that, provide very high performance storage at a low cost, very high performance compute at a low cost. And they're providing the industrial expertise for each individual industry that they work in. And an amazing history. They're a very innovative company, and it's great to work with them. And we love how those are coming together. And I think over time, together, we'll really transform the industrial space and kind of bring it. A lot of these program logic controllers and SCADA systems go back to the 70s, right? And so, kind of bringing them into the cloud connected world securely is really important in this space. Being able to do the edge processing is really important. You can't have a factory stop when somebody with a backhoe cuts your fiber. I think that continue to run, right? So edge processing that's where snowballs and outposts become really important, and green grass and edge processing and edge runner and some of the stuff that we provide out there, edge wise or site wise. So I think it's a really good partnership there, and I'm really excited to see where TwinMaker's going, and I'm really excited to see the amount of customers that are already on TwinMaker trying it out right now and starting to build their 3D environments and their dashboards and stuff for managing their smart factories. And then that kind of extends into the automotive world, where we're doing things with FleetWise, which allows you to manage fleets of vehicles and creates a data warehouse from the fleets of vehicles data that you're doing, which connects in with the snow cone to collect the ADAS data, which connects into the simulation to allow you to do your simulated worlds and test your autonomous vehicles in these virtual worlds, so you can run millions of miles in a virtual world and then do the machine learning, and then using FleetWise push those ML models back down to your cars again. So I think that kind of cycle is really exciting.
I've never thought about the testing and the actual like data streaming side of smart factories with the new 5G rollouts and potentially where we're going with 6G. So it makes a lot of sense that AWS would play pretty heavily in the space. Also, something that might be interesting for the electrical engineers listening, I heard that you recently partnered up with Ansys. Can you tell me what you're doing in the world of circuit design and simulation?
Yeah, so we're really excited about that. And again, this is an area where we're partnering with somebody who has the domain expertise and the history in that domain, where we're focused on sort of the scale out compute to enable their circuit simulations and all the simulations. Ansys does a whole lot of different types of simulation capabilities and handle the data, the storage, the high performance computing, and the HPC piece. Ultimately, I think in all these cases, we want to make it so you don't have to be an IT person to do these simulations. Basically, you just focus on being an engineer on what you're trying to solve, and let the cloud figure out how many instances to run and how much storage to use and what type of storage to use and what type of network to do, and whether it should run in an outpost on your site or run in the cloud. You shouldn't have to think about that. You have enough to think about when you're designing your logic circuits, your motherboards, your RS flip flops, or whatever you're doing is inside your digital design components. And then we're working on also advanced caching capabilities, which will let you seamlessly move data between your manufacturing environments or your design environments and the cloud, so you can burst into the cloud as you need as well, so you can leverage your capital assets you have in design locally in addition to the cloud. And then we're working with Ansys to try to make that just seamless. They're the experts in these areas, just like Siemens is the experts in industrial. Our goal is to handle all the heavy lifting of the compute, the storage, the transport, and the ability to generate and manage the ML models and things like that.
And you've done a lot more than just industrial. Your resume is wild. Can you give us the rundown of all the different roles and jobs you've had over the years?
Well, so with Army, I was sort of the CTO for personnel and logistics there. So I worked on everything from the Force 21 planning system, which was about sort of managing major regional conflicts and running actually on the edge a thing called the Force 21 manning system that would keep track on all these laptops in the field and synchronize and replicate to all these laptops in the field all of the movements of troops and the equipment in that space. And then we also worked on, as part of Force 21, the Oculus system, an ocular system, which was, it covered one eye and it enabled you to have topo map overlays and also do targeting. And so we worked on that. That eventually developed into the Apache Oculus that they use for aiming, where it follows the person's head,
Yeah.
and stuff like that. So I was pretty excited to see that evolve over time. And then I moved from working in the Army space to the Pentagon, where I was responsible for actually taking the entire Department of Defense through Y2K technically, which was a great exciting. But also I was the sponsor for DARPA and the JASONs, which was where I was helped to fund quantum computing and nanotechnology and MEMS, robotics, autonomous systems, and satellite systems. And in addition to boring, if you like boring stuff, it's exciting to me because of the scale, like the identity management. The military has about 250 logistics systems. Getting them to all work together was just amazing. And dealing with all the intelligence systems. And I was on the advisory board for the NSA, working for Keith Alexander for a long time as well. In that space, working on the scale and capabilities that they have was pretty amazing as well. So that was exciting. And then The work I did with NASA was on OpenStack. So it's totally
Oh,
different, not what you would expect. So I worked on some of the first OpenStack creation and deployment there in the early days with the Rackspace team as well, and sort of defining the requirements for OpenStack initially. That was while I was at Sun. And between Sun and my startup.
but it doesn't end there, obviously. So what was next for you?
I left from working at the Pentagon. I followed actually my wife's career. She's much smarter than I am, Sherry Steele. She was the head of the Electronic Frontier Foundation. And
Oh, really? Okay.
so we followed her career to California. And that's when I became the CIO at Sun Microsystems, and then eventually a business unit leader there as well. And Sun was, I worked for Scott McNeely. He was an amazing leader. It was a lot of fun doing that. I worked with James Gosling, who invented Java, who works for us here at Amazon. He also worked with me at Liquid Robotics. He was our chief software architect. And here he works on green grass and robotics and distributed processing and quantum computing. So he's a multi-domain distinguished engineer, just an amazing person. Very lucky to have gotten to know him and work with him there. So we kind of followed each other to a number of different places.
That's awesome.
Yeah, from working at Sun when Oracle bought us. So I left that and did the consulting at NASA on OpenStack and some other things like that. And then we went to, I was talking to my wife about what I should do next. And I said, I really wanted to do something either in nanotechnology, because I'd worked a lot in nano and MEMS at DoD, or in robotics and autonomous systems. And it just happened that, my career, I did a lot in the Department of Defense, and I did a lot in the oil and gas industry, and I did a lot in large scale computing. And I had a background in biology too. I was a marine biologist as well. So biology, geology, computer science were sort of my three things.
Yeah.
This company called Liquid Robotics contacted me. They were already a startup, a great group of engineers there, led by Mr. Hine. And so they had invented this incredible long duration autonomous vehicle called a wave glider. Their three big customers were defense, intelligence, oil and gas, and biology. Those fit well into my three areas, and it was robotics and autonomous systems. So we did set the Guinness World Record for the first autonomous system to cross the Pacific. No one ever will be the first again.
Yeah. It's amazing to be the first to do something, even if it's something kind of lame, let alone something amazing like getting an autonomous robot across the Pacific Ocean.
Yeah, it was very fun to do. We had to, in those robots, we had a plaque that everyone in the company had signed, and it carried it all the way to Australia, which was very cool. So it was great to have, because we wanted to really prove that these robots could run for a year in the ocean and could cross an ocean, right? And that's the ocean's a really hard place to work. You've got, salt water, electricity, and metal. Those three things together don't work well, right? Yeah. And you've got huge amount of G forces in the waves that it has to survive. It has to go through hurricanes, and we've been through multiple hurricanes at Liquid Robotics. Oh, and these fleets of robots all over the world. And you talked earlier about how the internet changes things. I would get paged about robots having trouble in Antarctica or in the Arctic, or for robots having trouble, off the coast of South Africa, or, because we had hundreds of them all over the world on missions, and they would be interacting with ships and interacting with, all sorts of things. And they'd be operating in fleets, or they'd be working in tandem with an oil company on exploration, or they'd be measuring, carbon absorption to the ocean, or they'd be doing anti-submarine warfare tracking, or they'd be doing all these different kinds of things all over the world. And I always wanted to know if any robot had trouble. I would get texts in the middle of the night that a robot's having trouble in Indonesia, right? And I'd have to connect with the operator, because they were autonomous, but each pilot would manage about 20 or 30 of them. And so they would call, if they got confused about where to go, they literally called them on their phone. And it was kind of funny. You get these calls from these robots. I don't know what to do. And they could right from their phone say, head this direction, head on this heading, right, or whatever. And
that's cool.
Thousands of miles away would turn and go the direction that they had said, and they could watch it on their cell phone. But I mean, this is where the internet world gets so amazing. And then,
wow,
James Gosling wrote the swarming algorithms and the navigation algorithms for it and rewrote the robotic operating system that was on the robots, the robotic platform that ran on it. It was all running. We used CAN bus for interconnect communication, and it was all running on ARM-based processors because it generated all its own power. So every milliwatt mattered.
Yeah.
And so we managed the power and stuff. It was a lot of fun to do that.
What a fun engineering challenge.
Yeah, it really is. And some of the things I learned there are like in this one of the reasons the snow cone can handle all of the impacts and weatherproof and all that other stuff in the snowball is because of what I learned in doing that at Liquid Robotics, right?
Mm.
And in addition to that, some of the stuff that we learned at NASA is also built into the snowball as well. Some of the shock absorption components as well. So and then also what I learned when I was CIO at the Pentagon, some of the stuff I learned in CTO for the Army about doing mil spec equipment also went into the snow cone and snowballs designs.
Who would have thought that all those things would have come together to turn into what you have now? And then coming totally out of left field is quantum computing. I understand you're working on some initiatives there. Can you tell me more about that? I love geeking out on quantum.
Yeah, so there's sort of three different initiatives in that space that we've got. So first of all, we're building our own quantum hardware. We've published quite a number of papers on our, it's called the cat qubit, as in Schrodinger's cat, those of you who are familiar with Schrodinger's cat. But we're creating sort of the first logical qubits that are error corrected, which is error correction is really the panacea in quantum computing, because you're measuring vibration and spin of atomic particles that you've entangled. And we can talk more about that. And just heat, for example, is vibration, which is noise. And so you have to remove that. So you're running at as close to absolute zero as you possibly can. And you're entangling these particles, and then you have to continuously error correct them. If you don't error correct them, just like with the classical computers like we're talking on now, you get error correction code in the memory and things like that. You have alpha particles actually do flip bits on your computer, but you've got ECC to correct it all the time. And then also you have defects in the fabrication process, although we don't think about that, but every chip has defects. And so designs work to route around those defects, detect and route around them, kind of like you do with storage and RAIDing and other things like that. You're always routing around defects. And so error correction is the panacea on a quantum computer, because as you increase the number of qubits, which we need to do, if you don't have enough error correction, the amount of noise increases exponentially, and then you lose your signal to noise and you don't get any good result, right? So I think that's important. It's really got to be about error correction. So we are building our own hardware, just like we build our own graviton processors here at Amazon, and we build our own Trainium chip and inference chip, and we build our own networking silicon and all those other things. So we do that. But just like we do here, we have great partners, Intel, AMD, and NVIDIA, for example. We have the other part of the quantum service is our partners. We have these amazing quantum computers available on AWS and available in real time. You can connect to them with our service called Bracket. And so Bracket lets you, in a Jupyter notebook, using Python, you can build a quantum circuit, and then you can execute that quantum circuit in a simulator to see how it works and make sure you're happy with it. And then you can execute it on each of our partners' computers with a common set of APIs. So we have a quantum annealer that's electromagnetic cryogenic. We have so it's using electrons, so it's for that as your atomic particles. We have Oxford quantum circuits and Rigetti, which are our two electromagnetic cryogenic gate-based machines. Again, you're entangling electrons. We just added Xanadu, which is the first photonic-based machine where you're entangling photons. We have IonQ, which is I think the leader right now in ion traps, and you're entangling metal ions in that case. And we have QEra, which is a Reinberg atom machine where you're entangling atoms, right? So you can build one API-based Jupyter notebook and execute on each of these. And we have a direct connect to each. It's an encrypted direct connect. We've gone through SOC 3 and SOC 7 with them. We've got, all of the things you would expect for these. They integrate with identity management and S3, and, you store your data on an S3. When we first did this, I texted my daughter and I said, today, we had the first time in history where one quantum computer called another quantum computer, passed variables between it on a cloud service.
That's cool.
And I said, you can remember this to tell your grandkids that your dad was involved at that very first time when they crossed each other.
What did
And
they say? Did they say like ahoy or like pull the Alexander Graham Bell move or?
Oh, so they were passing variables back and forth. They weren't saying, they were passing.
Okay.
We executed a circuit on one. It got a result.
Hmm.
We did some manipulation of that data and then executed a circuit on another one and got a result. So they were working together to solve a problem.
What I'm hearing you say is I understand there's a bunch of different types of quantum computers and
Right.
trapped ion, electron, whatever. Is this almost a layer up in the stack where you're able to almost be technology agnostic?
Yeah, that's what Bracket does. Is it provides you this API interface with a Jupyter notebook that lets you execute against all of these machines. And then when our machines start to come online, there'll just be another one of those machines in the list. Just like with, you can go onto EC2 and you can execute on an x86 AMD or an x86 Intel, or you can execute on an ARM-based Graviton, or you can execute on a GPU from NVIDIA, right? And so it's sort of the same thing. You could run the same Lambda function on all of them, right? If you wrote it in Java, right, you could write on all of them without any changes. With Bracket, you have this sort of common API interface environment will let you access all these machines. And I think we'll also have in the future with Bracket the ability to do specific things on each machine that are unique to them as well. So, because I think you'll want to dive deeper into how some of the machines have specific advantages in these architectures. And ultimately, we don't know which one will win. I mean, this is back to the days,
Right.
remember when we had all these different types of computers. And so, and nowadays, things are kind of, standardized around x86, ARM, and GPUs, right? That's kind of what you see. But if you went back, you had DEC Alpha, and you had MPPs, and you had x86, and you had ARM back then too. But then you had Spark, and you had HP, and you had AIX, and you had you had MPPs and mainframes and all this other stuff, right? And that's kind of where we are with quantum computers. You've got all these different technologies, and I think all of them will be good for something over time as we start as each of them start to specialize in the areas where their specific architecture works better. And so we wanted to give customers that choice, just like we do in our compute platform, give them a choice of multiple quantum computers and make them easy to access securely and safely and inexpensively, right?
Yeah.
They don't have to have a cryogenic system in their data center to test out a quantum computer, right? They just can log on for a couple of dollars and try it out on a real quantum computer, which is really exciting to me. And then
Really cool.
the third part of our strategy is we have a quantum solutions lab, which is a bunch of people who really understand how to program quantum computers, along with how to do advanced math optimization, which is most what people are trying to do with quantum computers. So they can help you solve optimization problems today on classical computers, in addition to show you how they will be solved in the future as quantum computers get more qubits, which are more error corrected.
Okay. So I'm fascinated by quantum, and I'm glad we were able to take some extra time to talk through it. You mentioned the 25-year cycle. I think we're in such a rare time where we get to see all these different competing technologies, and it almost sounds like with the AWS systems, you can essentially build out a fleet of different computers that are good at different types of things, and based on the task at hand, you can use a combination of different technologies to solve a challenge. Yeah.
You do that with classical computers, right? You farm off to a
Yeah.
GPU to do your graphics processing and some ML processing, or you farm off to Trainium to do ML processing, which is specifically designed for ML processing. You do your general computing on x86, either ARM or AMD, right? Or either Intel or AMD, and then you do general purpose processing on the ARM processors as well, Graviton and things like that. So you can choose all these different compute platforms, just like you've different types of storage, block and object and file-based storage, right? And so you can choose what's best, just like you can choose from multiple databases. And if you look at machine learning, there's lots of machine learning models, right, that you can choose from, and some of them are optimized for different things. And so I think that choice is really important. And I think as a cloud provider, we want to provide choice. And I'm very excited about what our quantum partners have achieved and continue to achieve. And we'll continue to work on our machine just like we work on our graviton processor as well. But we're going to 100% support our partners and full access to those partners for our customers, because that's what our customers want, is the ability to have those choices.
What technology is the AWS system using?
For our quantum, it is also an electromagnetic cryogenic machine. So we're entangling electrons as well, which is also what IBM and Google are using as well. So that's a very popular one. One, because it's rather mature. It's been around for a long time, but it's also very fast. You can process multiple circuits. Some of the other machines are slower but more coherent. So the circuits stay more coherent, or in other words, have less noise for longer periods of time, but they are slower to get started. And then there are both gate-based machines and annealers. And so those are also solve different problems in different ways. Gate-based are more general purpose processing, and annealers are more around optimization processing. So, and like D-Wave's been very successful in that space, and you'll see those. And then QEra also is coming up in that space as well. So it's exciting to see all these technologies in parallel. And I think people really need it. Now is the time to start understanding how to write quantum algorithms, because they are going to be transformational in the future. I think, there's a lot of hype about quantum right now. I think when I look at the hype on quantum computer, it's like 25 years from now is when that hype will be true. So don't believe it now. But every month there's new breakthroughs. Every month the number of qubits available that are error corrected is getting better. And so we're starting to see, we can see the light at the end of the tunnel for quantum advantage in the next few years. So we're pretty excited about its choices.
You'll have to rethink the triple encryption on the snowballs.
Yeah. So that's an interesting one. So just put this in perspective. Our goal right now with most quantum computers is to focus on a Hamiltonian simulation of a molecule, because that's molecules work using quantum technology, or quantum physics. And so a quantum computer is a great way to simulate a molecule. And for material science, that's incredibly valuable. And we can provide a pretty amazing set of things we could get done with, say, 1,000 error-corrected qubits, right? That would be a miracle to have that, because we could do Hamiltonians on ammonia and a whole bunch of other things, like figure out room temperature superconductors, and like better batteries and better solar panels, and how to produce ammonia to lower energy density, and all these kinds of things you could figure out in that space. And that's really, I think, the near-term thing. To break Shor's algorithm, you're talking about 2 million error-corrected qubits.
Oh, okay.
The largest machine right now is 127, just to put that in perspective, right? So it will happen, and that's why you should be using Kyber, which you can do on AWS today. You can do post-quantum in cryptography just by clicking a switch, and you can protect all your transport data with post-quantum cryptography, so that if someone is collecting that data, they won't be able to decrypt it in the future. Right. And so we recommend that you start using that post-quantum cryptography now for your transport. But it's going to be a while before that happens. But it's definitely a concern, and it's something that we should all be watching. But all encryption is fleeting, right? I remember when 52-bit encryption was good enough, and then that was able to be broken by machines. And then now we're at 4096 for key exchange and 256 for general, and those kinds of things. So I think those will continue to be attacked by more and more classical compute power, and we'll continue to move up the stack there. And then as quantum computers get to the millions of qubits, then post-quantum cryptography algorithms are going to be really important. And quantum key distribution, that's one way to protect against a quantum computer, is quantum key distribution and quantum networking, which is another area we're investing in as well. So it's exciting.
As we wrap up, we like to do a couple lightning round questions. You mentioned that Spock was a big influence on you. Are there any pieces of pop culture or science fiction that really get the future and the technology right, and any that just really get it wrong?
Oh, that's interesting. So there's an Arthur C. Clarke called Rendezvous with Rama.
Love that one.
And it's a great book because the Ramans do everything in threes, and I do everything in threes. There's 3 layers of networking everywhere. There's 3 layers of encryption. There's 3 layers of anti-tamper. There's 3 layers. Our availability zones in our regions have 3 availability zones minimal, with 3 layers of network encryption and 3 layers. So that doing everything in threes, I think, is a great idea. And three is a natural number for high availability, and so it's five. So load balancers are five, and redundancy in threes is sort of your n+1. So I think that was a great book, a great inspiring book to think about how to engineer things to never fail.
Yeah.
It's a great ending of that book, which I won't disclose for people who haven't read it. I think A Brief History of Time by Stephen Hawkins was another book. It was the first book I ever ordered on Amazon, by the way, and I think it was another interesting to get a good understanding. I think everybody should read that and get a better understanding of how the universe works to as much as we understand it.
Is Star Trek in there for you?
I think, I like Star Trek a lot. I think it's one of the most fascinating thing that I could relay about Star Trek. I was watching one of the set designers, and they asked the set designer, well, how did you know that everything would be touchscreen? This was on Next Generation. And they said, well, putting switches like in the old Star Trek, buying all those switches from Radio Shack and putting them in was really expensive. So we just did paint on the back of glass, and then people pretended they were touching the screen. So really, all of the iPhone and the tablet, all that stuff was just to save money. It inspired all that. Initially, it was just to save money, but it inspired all of the touch screens we have today. We're based on the set designer trying to save money. A funny turn, because all of us were inspired to go make those things real, right? From seeing that, and I think that's also one of those areas that is fascinating, how that has occurred.
Well, we're way over time, but I probably could have gone another 2 hours.
Yeah, there's just a lot going on in all these different spaces. So, but thank you for the time, Daniel. It was an interesting discussion.
Woo! Now that is how you wrap up a season. That was Bill Vass, VP of Technology and Engineering at AWS. And fear not, we'll be back soon with Season 5. So make sure you're subscribed to the Moore's Lobby in your favorite podcast tool so you don't miss it. And also check out Moore's Lobby on social. Finally, please share this podcast with someone you think will enjoy it. That's how we grow and keep this thing going. I'm your host, Daniel Bogdanoff, and I'll be right back here with Season 5. I can't wait to see you then.